Last lesson we introduced the method of substitution for integrals that are a little bit trickier, that don't seem to fit any of the common rules. In this video we're going to be still using substitution but looking at definite integrals. And once again we'll do two examples. The first is the integral between 0 and 2 of x squared outside root x cubed plus 1. And we're going to use the substitution u equals x cubed plus 1. So let's look at the relationship between du and dx by deriving this equation. We get 3x squared. And so we notice that du is equal to 3x squared dx. When we look at our original integral, however, we only have x squared dx. So you've got options. Either you can continue modifying your working out over here. So we might multiply both sides by 1/3. And if we do that, then we get x squared dx on the right hand side, just like we have here. Alternatively, you might take your original integral and adjust this. So we could introduce a 3 in here and compensate with a 1/3 out the front. Either method is completely fine. Now the only thing that is different from what we did last time is that we're dealing with definite integrals. And so we also need to adjust the lower bound and the upper bound because these are in terms of x. So if x is equal to 2, what's the corresponding u value? Well, using our substitution equation, u is equal to x cubed plus 1. And in this case, our x value is 2. Evaluating 2 cubed plus 1, well, 2 cubed is 8. And so when we add the 1, we get u equals 9. And for x equal to 0, we get u is equal to 0 cubed plus 1. And this is simply 1. So we can now update our lower bound and upper bound to be between 1 and 9. So rewriting our original integral, we now have the integral between 1 and 9. The x squared dx is being replaced by a 1/3 du. And so we'll put the 1/3 out the front. And we have the square root of x cubed plus 1. So that is simply the square root of u. Even though there's a little bit more work in adjusting the lower bound and the upper bound in these kind of questions, the good thing is that because it's a definite integral, we actually don't need to change back at the end. So what do we have here? Well, u to the half, we know that when we raise the power, we get 3 on 2, and it's over 3 on 2, or so we could say 2/3. And writing this in radical form, u to the power of 3 on 2, well, that is the square root of u all cubed. In previous examples, we have done the square root of u cubed, but in order to evaluate this mentally, it's probably easier to set it up like this. If we bring out the 2/3, this can make our calculation a little easier. So the 2/3 and the 1/3 give us 2/9. And then evaluating, we get the square root of 9 all cubed minus the square root of 1 all cubed. Since the square root of 9 is 3, 3 cubed is 27, and, well, the square root of 1 is 1. When we cube that, you get 1. And so we have 2/9 times 26. This gives us 52 over 9. And if we wanted, we might like to write this as 5 and 7/9. And that's our solution to example 1. Okay, example 2. Find the exact value of the integral between 0 and pi on 6 of cos x to the power of 4 times sin x dx. We are going to use the substitution u equals cos x. So first, the relationship between du and dx. The derivative of cos is negative sine of x. Now we can see in our original integral that we just have sin x dx. So since we just want sin x dx, let's take that minus and put it over with the du. Now we also need to adjust our limits. When x equals pi on 6, u is going to be cos of pi on 6. Remember, this is our relationship between u and x. And what is cos of pi on 6? Using our exact values, this is the square root of 3 on 2. And when x is equal to 0, what is cos of 0? Well, whether you use the exact values, so to speak, or you think of your cos graph, cos of 0 is 1. This means we can now rewrite our integral. Instead of our limits being 0 and pi on 6, they are now 1 and root 3 on 2. Instead of cos x to the power of 4 is now just u to the power of 4. And our sin x dx gets replaced with minus, I'll just put that out the front, du. Evaluating, we get u to the power of 5 on 5. And now all that's left to do is apply the fundamental theorem of calculus. So first of all, we are going to substitute in root 3 on 2. Then we are going to substitute in 1. A little bit nicer. Now let's think about this root 3 to the power of 5. Root 3 squared just gives us 3. So if we think about root 3 to the power of 4, root 3 to the power of 4 is root 3 squared squared. So that's just 3 squared, or 9. But then we have one more root 3. So this means that we have 9 lots of root 3, and on the bottom we have 2 to the power of 5, which is 32. Over here we simply have minus 1/5. All that's left to do is tidy this up. We notice that when the 5 and the 32 multiply, we'll get a value of 160. To then incorporate this minus 1/5, we need to make that the same denominator. So 1/5 can be rewritten as 32 over 160. The minus and the minus out the front, that makes a positive. So I'll write this 32 on 160 first, and then we simply take away this minus, take away this 9 root 3 over 160. But it's all one fraction. putting it in the middle looks a bit nicer, and there we go. That's the exact value solution to our second example. Great work.